In this video, we're going to revisit Thevenin's theorem, and we're going to see how to apply it to AC circuits. So I'm going to begin with the DC circuit just to remind ourselves what Thevenin's theorem tells us about simplifying a circuit like this down to a much simpler equivalent circuit. So in my example circuit here, I've got a total of 14 elements. So there are 10 resistors, 2 voltage sources, and 2 current sources. So 3 different types of element, but a total of 14 elements. If we were to look through the circuit here, we can identify a total of 11 nodes. So I've actually numbered the nodes in the diagram here. I call this one N0. This one here is N1. This is N2. N3. This part of the circuit here. And so on, all the way up to N10. So of those nodes, 5 of them are true nodes and 6 are binary nodes. So just to remind you, what we mean by a binary node is it's a node where only 2 elements meet. So for example, N2 here is an example of a binary node. Conversely, a true node is where 3 or more elements come together. So if you look at N3 here, we've got this current source and these 2 resistors meet. So that's 3 elements meeting at N3, so that makes it a true node. Similarly, N9, there are 3 elements meeting here, so N9 is a true node. Now the reason nodes are important here, and the reason that I'm reminding you of them, is that a lot of what we're interested in a circuit like this is the node voltages. So it's the voltage at a particular node relative to some reference, or the voltage between 2 nodes in the circuit. I've also counted the branches here. There's a total of 9 branches. So what we mean by that is just the parts of the circuit, any path in the circuit that begins at one true node and ends at another true node without passing through any other true nodes. So you can go through a binary node here. This would be one branch here, but it must begin and end at a true node. Okay, so it's kind of a complicated circuit. There's a good few bits and pieces in there. But what Thevenin's theorem told us was that we could replace all of this with a much simpler equivalent circuit consisting of just a voltage source and a resistance. And I'm going to connect it at its interface. I'm going to provide the same 2 terminals, which I'll label A and B again. The names that I'm going to give these are VTH for Thevenin voltage and RTH for Thevenin resistance. And the idea is that if this circuit here was placed inside a box where you couldn't see what the circuit was, and the only thing that was visible at the outside of the box were these 2 terminals A and B, which are connected to nodes 3 and 4. No matter what you did here to explore the electrical behavior of the circuit, you could connect voltmeters, ammeters, impedances, voltage sources, current sources, whatever you want to do out here in order to see how the circuit inside the box responds. You won't be able to tell the difference between this complicated circuit here and this much simpler equivalent circuit. So for a DC circuit, anything inside the box, as long as it's made up of just these voltage sources, current sources and resistors, no matter how you connect them together, no matter how many of them there are in there, it can always be replaced by this much simpler equivalent circuit, which from the perspective of an observer at AB behaves electrically the exact same. Right. Now, of course, there's a lot of stuff happening at the individual nodes and branches inside the circuit here, which is not being reproduced here. So if the observer has access to those things, clearly there's a big difference between electrically between what's happening here and what's happening here. But just from the perspective of these terminals A, B, if that's all you have access to, you might as well have this rather than this whole circuit here. Now, of course, you must have the correct values for VTH and RTH in order to reproduce the behavior of this circuit. So the question is, how do we choose the values of VTH and RTH? Well, what the Thevenin voltage, VTH, is the open circuit voltage at AB. So it's this voltage here when A and B aren't connected to anything. So I'll actually just label that in here, VTH. So if we don't connect A and B to anything, they're just left open circuit. And if we were able to measure the voltage between these 2 points, that's what VTH, that's the value that VTH needs to have. RTH, the Thevenin resistance, is the resistance between A and B when all the sources are set to 0. Now we have to be careful exactly what we mean by sources set to 0. The two different types of sources that we have here, voltage and current sources, are going to behave quite differently when they're set to 0. So a voltage source becomes a short circuit. And a current source becomes an open circuit. So if we just pause to think about that for a minute, if a voltage source, normally a voltage source defines the voltage between the two nodes either side of it. So if that voltage is reduced to 0, it effectively just means the two nodes have exactly the same voltage. Then more or less you can think of it that they just merge into a single node. So this becomes like a piece of wire that just connects the two nodes together, so they become one. On the other hand, if you've got a current source, so current source defines the amount of current flowing through that branch in the network. If a current source is reduced to 0, it means there's no current flowing along there. So it's basically open circuit. So it's as if you just plucked that element out of the circuit and there's no path for current to flow through, so it becomes an open circuit. So the idea is, in order to calculate your Thevenin resistance, you remove or you set to 0 all 4 of these sources following these rules here. And then that leaves you with a network made up of just resistors. And you can combine resistors in series and parallel and whatever else you want to do in order to calculate what is the equivalent resistance between A and B. And once you have it, that's what RTH is. So that's how you would do it for a DC circuit. Now the good news is that we can basically do the exact same thing for an AC circuit if we're applying a phasor analysis to the circuit. So let's just think for a minute. These would be the elements that we would likely encounter in an AC circuit. So we're still going to have voltage sources and current sources, but once we're talking about phasors, these will be sinusoidal sources. So they're going to have whatever the frequency of the AC circuit is, these will be producing sinusoidal output at that frequency. If these are represented as phasors, then a single complex number will represent the magnitude and phase of the sinusoid that each source produces. Then the other elements that we're going to see are resistors, inductors and capacitors, so RLC elements. And all 3 of these can be replaced or represented by impedances. So if we just think, what do we mean when we talk about an element in a circuit? Really what the element represents is a particular relationship between the current and voltage either side or across that element. So for example, in the case of a voltage source, what this element in a circuit tells us is what the difference in voltage is between the nodes either side of it. So here I've written that as V, and the current through it is I. But V is just going to be equal to whatever the value of the voltage source is. So it doesn't change depending on the amount of current that passes through it. Similarly, for a current source, what that tells us is the amount of current flowing through it, which is going to be set by whatever the value of the current source is, and it doesn't depend on the voltage. So it doesn't matter how much voltage you apply either side of this. You could have a positive voltage, negative voltage, big voltage, small voltage. The current through here is just going to be controlled by IS. and it's always going to be determined only by that and doesn't get affected by the voltage. Now conversely, these elements here, the passive elements, what these elements are going to do is they define some relationship between the voltage across the element and the current flowing through it. So the most familiar of these, of course, is the resistor. V is equal to IR. So Ohm's law tells us the relationship between voltage and current in a resistor. They're proportional to each other, and the resistance R is the constant of proportionality. For an inductor, we have V is equal to L di by dt. So what that tells us is that the voltage across the inductor is proportional to the rate of change of current flowing through the inductor, and the constant of proportionality is the inductance in henries, which is L. The capacitor is like the opposite of that. We have I is equal to C dV by dt. So in a capacitor, the current is proportional to the rate of change of voltage across the capacitor, and the constant of proportionality is C, the capacitance in farads. So these are our passive elements, the RLC elements, and all of these can be represented as impedances when we're carrying out a phasor analysis. However, we need to know how to convert each one of these into an impedance. So for the resistor, it's very straightforward. The impedance of the resistor is exactly equal to its resistance. So nothing to calculate, you just put in the resistor value, that is your impedance. And it doesn't depend at all on frequency, which the other two are going to. So for the inductor, the impedance of my inductor, let's call it ZL, is equal to J omega L. Now, what do we mean by J here? Well, just in case there's any confusion, J here is the square root of -1. So what a mathematician might write as I, but I'm going to use J, the superior electrical engineer's notation for imaginary numbers. So J is the square root of -1. In our circuit here, we'll imagine that there's a frequency F, which will be in hertz. And we'll see this in some of the example questions once we get to that point later in the video. So imagine we have a frequency F, and that's going to be the same frequency throughout the circuit. So any sources that are in our AC circuits are all going to have the same frequency for the examples we look at here. And that frequency will be specified in hertz. So what omega is the angular frequency. So it's the same, it's telling us the same physical property of the circuit, like how many oscillations per second basically are occurring in the electrical signals, but it's measured in different units, so radians per second. So 2 pi F is how we calculate omega from F. So this is the Greek letter omega. Looks like a W, but it's an omega. So that's 2 pi F. So the formula that I have here, J omega L, we can see firstly that the impedance of an inductor is an imaginary number because it's two real numbers multiplied by the square root of -1. It also depends on frequency. So how much an inductor impedes the flow of electric current depends on how fast that electric current is oscillating. So the impedance depends on the frequency. And then finally we have for the capacitor, ZC I'll call it, is equal to 1 over J omega C. So again, you can see that the impedance of a capacitor is going to be an imaginary number. It also depends on frequency. However, in this case, the frequency appears in the denominator of this fraction. So it actually means that the impedance gets lower as the frequency goes up. So a capacitor impedes a signal less if the signal oscillates faster. Now you can also write this as -J over omega C. It's the exact same thing, just rewritten a different way. It's like multiplying this fraction here by -J over -J, and this is what you end up with. So these are important when we're analysing AC circuits. We need to know how to represent each element in our circuit as an impedance, and I'm going to make use of these when we're calculating the Thevenin circuits in the examples in a minute. So all three of these elements can be represented as impedances. Once we've converted everything in an AC circuit into impedances, well, all of the RLC elements, into impedances, then we can use all the same tricks that we would use with resistors in a DC circuit. So we can combine impedances in parallel or impedances in series. We can apply things like Thevenin or the closely related Norton equivalent circuit. So there's lots of different things that we could apply in order to simplify and solve different circuits. So let's see an example circuit and how we might go about doing that. Let's park this one here for a minute. So here's an example of an AC circuit. Again, you can see there's a bit of a mess of different elements in here. But one key thing to notice is that the three sources that are present, these two voltage sources and this current source, they all have the same frequency. So they're all 50 Hertz. Now, I haven't specified the exact values of these, VS1, IS1 and VS2. I'm imagining that they're phasor values, so complex numbers. But the important thing is that they all have the same frequency. So one of the properties of RLC circuits is that because they're linear, we're not going to observe a voltage or a current anywhere in the circuit that has a frequency other than 50 Hertz, because the only things producing voltage and current in the circuit are all 50 Hertz sources. So all the currents and all the voltages in this circuit are going to be 50 Hertz AC. We're going to be able to calculate a Thevenin equivalent circuit for this by replacing all of our passive elements with impedances, and representing these sources as phasors, and then calculating the Thevenin equivalent circuit the same way that we would have done for a DC circuit. So here I've just shown what it looks like when I replace every resistor, capacitor or inductor with an impedance, and I've just represented the impedances as these kind of rectangular blocks. You'll sometimes see people use these to represent resistors, but they're also commonly just used to represent impedances, which could be resistors, inductors or capacitors, or it could be a mixture of resistance and reactance. So some combination of resistors, inductors and or capacitors could be represented by one of these blocks here. So initially I've just taken each element and converted it into one impedance, but we can also go through a circuit like this and we can merge these into single equivalent impedances the way we would with resistors. So like these two, for example, are in series, so I could add them together and replace them with a single equivalent impedance, even though the actual original elements aren't the same type of element. Now it's important to remember there must be a single frequency in the circuit, and the equivalent circuit that we come up with for the AC circuit is going to be specific to the frequency that we calculated the equivalent at. So all of these impedances, well, the ones for the capacitors and inductors are going to depend, their value will be different for different frequencies. So if I was to change the operating frequency of the sources here, some of these impedances would change, and therefore I would need to recalculate the Thevenin equivalent. Also, if I had sources with different frequencies, we'd need to deal with that carefully. You couldn't represent it with a single simple Thevenin equivalent circuit like the way I have done here. There are ways that you could use Thevenin even in a circuit that had multiple frequencies, but it would no longer be the simple picture that we're talking about here. But so much of the time when we're dealing with AC circuits, they're going to be circuits that are operating at a single frequency. So for example, in a power circuit, we might be operating at mains electric frequency, and just the whole circuit is going to be at that frequency, and therefore this can be a very, very useful tool to have in our box to be able to actually analyze those types of circuits. So for each element that I've converted here, I've just applied the same rules that I showed on the previous page. So each resistor just becomes an impedance which is equal to its resistance, and then the capacitors and inductors are converted using these formulae that I wrote. And just remember that it's always going to be angular frequency that we use here, which is 2 pi f. So if f was 50 Hertz, that'll be 2 times pi times 50 radians per second, and that's what omega will be. Okay, so I think we're ready probably to take a look at some of the questions from the weekly quizzes. I suppose just before I let go of this page, maybe just worth reminding ourselves how we actually calculate what VTH and ZTH are. So they're going to be done exactly the same as they would be for a DC circuit. So to calculate VTH, we just analyze this circuit with AB open circuit. So we use the phasor values for each of the sources, and we use the calculated impedances for each element here. And we would analyze this circuit to calculate what voltage we see between these two nodes. And whatever we end up seeing there, it'll be a phasor, so a phasor voltage, and that's what VTH is going to be. And then we would set all of our sources to 0. So this would become just a wire. This would become just a wire, like a short circuit. This would become open circuit, so that entire branch would essentially just vanish out of the circuit. And then we could analyze with the remaining impedances. There would be nothing but impedances in the circuit. We could combine impedances in series and parallel and so on to simplify down and calculate what's the impedance remaining between A and B. And that is what ZTH would be, the Thevenin impedance. So that's how we do it. So let's take a look at one or two of these quiz questions. So I'm in the weekly quiz here, which is on Thevenin AC circuits. I'm currently on question 1. Actually, question 1 is a very simple one. It doesn't require any calculation really at all, but let's just see why that is. So you can see that the circuit is actually a good bit simpler than what I had drawn on the page there. We've just got 3 passive elements, a capacitor, inductor and resistor, and a single AC voltage source here. But the key thing is you're only asked for the Thevenin equivalent voltage in this circuit. So you're told the frequency is 200 Hertz, and you're just asked calculate what the Thevenin equivalent voltage would be if I was going to replace all of this with a Thevenin equivalent circuit of just a voltage source and a resistance. And actually, when this is open circuit, there cannot be any current flowing through this resistor here, because A is like a dead end, right? So there's nowhere for current to actually flow through this resistor too. Therefore, the current through the resistor is 0, and Ohm's law tells us that if the current in a resistor is 0, then the voltage must also be 0. Now, if there's 0 voltage across this resistor, that means that the voltage at this node here is exactly the same as the voltage at A, because there's 0 volts difference between them. So therefore, whatever voltage is present between A and B, that's the exact same as the voltage between here and here, which is just the voltage produced by the voltage source here. So actually our Thevenin voltage, which we observe between A and B, is going to be exactly equal to this voltage here. So if we look through our list of options here, you can see we've got 4 options. One of them is exactly the same as this voltage source here, so that's the one we're looking for. 5 volt magnitude with an angle of 2.1 radians. So that's the phasor value. So that's the first one. That's all you need to do. There's no calculation. Let's take a look at the next question. Hopefully the next one should be a bit more challenging. So, okay, in this case here, similar sort of looking circuit. The voltage source here is on the left, and then we have 3 passive elements, 2 resistors and an inductor. You're told that the frequency is 800 Hertz. And again, you're asked to calculate the Thevenin equivalent voltage. So if you were converting this to a Thevenin equivalent circuit, there's 2 things you would need to calculate: the Thevenin equivalent voltage and the Thevenin impedance. So we're only asked for one of them here, and we're given 4 options. So the way I'm going to go about this is I'm going to convert those into impedances. Let me just pull out a new sheet here. And I'll move this guy over to the left. And so just so you can see what I'm writing here on the left, I'll just put that beside the circuit on the right. So we have our voltage source. I'm going to use a slightly different symbol to represent that compared to what's shown here in the circuit diagram, but it's still just the voltage source. And then I've got one impedance, second impedance, third impedance, which is going to represent that inductor, the terminals A and B. So I'm going to call these Z1, Z2, Z3. So Z1 and Z2 are going to represent those two resistors. So maybe I'll just write in brackets here what these actually represent. Let's call this one R2. And I'm going to call the voltage source Vs. And we're interested in calculating what is VTH, which is going to be this voltage here. So to get the Thevenin voltage, again, you leave the terminals A, B open circuit, and then you calculate what the voltage is between them, and that tells you what the voltage source in your Thevenin equivalent circuit is going to be. So I have Octave open here, so I'm going to use Octave to do the calculations here. And in Octave, I've shut down a lot of the smaller panes because I'm not going to be using them. So I just have two of the panes open here, the command window and the editor, which appear in these two different tabs here. Now you could just type in the calculation directly into the command window line by line, but so that I can reuse the sequence of steps that I'm going to do, I'm going to record them in an M file and then just run the whole batch of commands all at the same time, and I'll be able to rerun them over and over then if I need to change them. So this is going to be a very sort of standard approach that I use for AC circuits, and this is not specific to Thevenin equivalent circuits only, but it's a good systematic approach, I think, to analyzing AC circuits using Octave. So this would also apply the same in MATLAB. So the first thing, I always begin by defining the frequency, assuming I know it. So in this case, the frequency is 800 Hertz. And then I convert that to omega. Now there is no omega key on my keyboard, so I'm using lowercase w, but that's representing omega. So it's equal to 2 times pi times f, the frequency. So that's going to be the angular frequency in radians per second. Now I need to put in my voltage source. So this is a complex number, which is the phasor value of this voltage source here. So in the quiz, it's provided to you in the form of a magnitude and an angle. So it's in polar form. It's a complex number in polar form. So it's the phasor representing this sinusoidal voltage source. So the way that I enter this in Octave or MATLAB is I write the magnitude of the phasor multiplied by, and then I use the exponential function. Then the angle, the phase angle of the phasor, multiplied by j. Now this is a little bit subtle what's happening here. If you haven't seen this before, this might look a bit confusing. The exponential function is e to the power of whatever's inside the brackets here. So this is used a lot in numerical programming, right? It's basically just saying raise the mathematical constant e to the power of whatever we have inside the brackets here. But the interesting thing is that if e is raised to the power of an imaginary number, it always produces a complex number of magnitude 1, exactly magnitude 1. And with this angle, whatever the size of the imaginary number is going to determine the angle in radians of the complex number. So this thing here is a complex number with the angle we want, but with a magnitude of 1. So we multiply that by the actual magnitude that we want in order to scale it up to a 15 volt phasor. So that's Vs. What else have we got? So I'll put in my original element values. Now I'm going to use another little trick here. So for the first resistor, that's this one here, it's 7.5 kilo ohms. So I'm going to write that as 7.5 E3. So this notation here is available to us in Octave and MATLAB. It's also available in C and probably a lot of other programming languages as well. It's effectively like scientific notation. So it's saying to take this number here and multiply it by 10 to the power of 3. That's what this syntax means. So in this case, I'm saying multiply 7.5 by 1000 because it's in kilo ohms. So that's 10 to the 3. My second resistor is just 220, and the inductor, which I'll call L, is 68 times 10 to the minus 3 because it's millihenries. That's this one here. Now, once I have those element values, I want to convert those into impedances. So let's jump back again to here just so we can see what I'm going to do here. The impedance Z1 is just going to be equal to R1. The impedance Z2 is just going to be equal to R2 because they're both resistors. And the impedance Z3 is going to be J omega L. And remember that we know in this case F is equal to, was it 800? Yeah, F was 800, which means omega is going to be equal to 2 pi times 800. So we can calculate all of these impedances now. What we can also say, looking at the circuit here, is similar to the last question, Z3 here arrives at a dead end when you get to A. So we know that the current through it has to be 0. So therefore the phasor, if the phasor current through it is 0, then the phasor voltage across it has to be 0 as well, which means that the voltage from here to here is exactly the same as the voltage from here to here. So this is VTH here. So it's sufficient for us to calculate the voltage across Z2. Now that makes our job very easy here, because we can say VTH is equal to, just applying voltage division, Z2 over Z1 plus Z2 times our source voltage here, Vs. That's going to give us our Thevenin voltage, which is what we're looking for. So let's put that in. Z1 equals R1, Z2 equals R2, Z3, excuse me, is equal to J omega L. And finally VTH is equal to Z2 divided by Z1 plus Z2 multiplied by Vs, our source voltage, and that will give us the value of VTH. Now I'm going to add in the Thevenin impedance calculation as well, even though we're not asked for it in the question, but I'll come back and do that in a second. First, let's save this as an M file. So I'm just going to save it in my home folder, which is Home's Ubuntu on this machine. I'll just save it as Thev, short for Thevenin. And it's going to apply the file extension .m. So once that's saved, you can see in the tab here it says thev.m, and I'm going to switch to the command window to run that so that I can see the output. So I'm still in Home's Ubuntu here, so I can just type thev, and here it is running the program. So you can see it writing in the values into all these variables. Here's where it calculated the complex number. That's a magnitude of 15 volts with a phase angle of 0.1 radians. Now you can see that it's shown here in Cartesian form, so as a real and imaginary part, even though we entered it in polar form here. So the kind of native representation in Octave for complex numbers is Cartesian form, and one of the problems that causes us is that when we finally see our Thevenin voltage down here, it's in Cartesian form, whereas the answers that we're trying to compare it to over here are in polar form. So that's no problem though. We can access the magnitude and the phase of a complex number in Octave as follows. So I can write ABS, which is short for absolute value of a complex number, in this case VTH. That'll give us the magnitude of the number. And then to get the phase angle, there's a function called angle. So angle of a complex number, and we can see here the magnitude is 0.427 volts, that's 427 millivolts, and 0.1 radians is the phase angle. So if we look at our possible answers here, you can see this one here is a perfect match, the top one, so that's A. So that's the correct answer to the question, right? Now, we're not asked for it here, but I'm also going to calculate the Thevenin impedance just to show you how that would be done for this circuit. So back to the circuit here. If we were calculating our Thevenin impedance, we need to set the sources, which in this case is just one source, to 0. And then we're going to calculate the impedance looking into the circuit from AB. So this is a voltage source, so when we set that to 0, it just becomes a short circuit. So here's A, B, and we're interested in the impedance looking into the circuit from over here. That's going to be ZTH. Z1, Z2, Z3. So you can see here Z1 and Z2 are in parallel with each other now that Vs has been set to 0. These two elements have now ended up in parallel with each other because they both begin and end at the same two nodes. So we can basically say almost right away Z3 plus the parallel combination of Z1 and Z2. So the total impedance here is going to be Z3 plus the parallel combination of these two. Now to combine two impedances in parallel, it's just the same as it would be for resistances. So that's going to be Z3 plus product over sum. Just like you would do for two resistors in parallel. And that's going to give us the value of ZTH. So back in Octave, I'm going to switch to the editor and I'm just going to add that bit in at the end. So ZTH is equal to Z3 plus Z1 times Z2 over Z1 plus Z2, product over sum. And save the file, and I'm going to run it again here. So Thev to run the file, and you can see it's got the same answer again for VTH of course, but it's now added on the end of it here, ZTH. So you can see that ZTH is a complex number as we expect, because it's a mixture of this inductor and then parallel combination of these two resistors. It's shown here in Cartesian form. If you wanted to get it in polar form, you could do the same thing that I did before. You could get the absolute value of it, and you could get the angle of it to get the phase of it. So if that's what you were asked to do. So in this case, it has a magnitude of 403.13 volts and a phase angle of 1.012 radians. So I'll just do one last question here. What are we on there? That was question 2. We'll just take a look at question 3 here. And we'll see how quick it is. Once we have a file prepared for one of these, we'll see how quick it is to adapt it to a new question. So here's question 3. So this one is quite a simple looking circuit, but it does contain both a resistor and a capacitor. So we still have a voltage source here, and again you're asked for the Thevenin equivalent voltage in this one here, and the frequency of operation of the circuit is 900 Hertz. So for this circuit, there isn't really much to explain here. It's like the voltage that you're going to see here when the terminals are left open circuit is just going to be the voltage across this capacitor here, and we can get that by voltage division between these two. So we represent the two of these as impedances and then do voltage division to get the voltage across the capacitor resulting from this source here, and that will tell us the Thevenin voltage. So I just go back to my M file here, and I'm just going to modify this one. You could save this and make a new file and copy and paste this in, but I'm just going to overwrite what I had for the last question. So my frequency I'm going to change to 900 Hertz. Omega is still going to be 2 pi f. The voltage source in this case has a magnitude of 30 and a phase angle of 0.6. There's just one resistor in this circuit, and it's 75 ohms. And we have one capacitor, which is 24 microfarads. So 24e minus 6, that's 24 by 10 to the minus 6. Let's call these ZR and ZC in this case. So ZR is just equal to R. ZC, applying our formula from before, that's 1 over j omega c. And we can get VTH by voltage division then. It's going to be equal to ZC over ZR plus ZC times Vs. Now for ZTH is going to be a little bit different here, because in this circuit, if I was to set my voltage source to 0, this would become just a wire, so short circuit this, and what we'd end up with is the resistor in parallel with the capacitor. So if we were to look in from the direction of AB, once that source is zeroed out, we would just see the parallel combination of these two as the impedance between A and B. So I'm going to put in ZR times ZC over ZR plus ZC. So that's the parallel combination of ZR and ZC, and that gives us ZTH, the Thevenin impedance. Okay, so back to our command window, and I'll run that again. So to run an M file, you just type the name of the M file without the .m extension. And you can see that it's updated all those variable values. We've got 900 Hertz, got the angular frequency in radians per second, our voltage source there as a phasor, and you can see it's in Cartesian form here, but it looks about the right size for our 30 volt magnitude and our 0.6 radian phase angle. And we've got the resistance, small capacitance there was 24 microfarads. The impedances of those two elements, so ZR is just the same as OR. ZC is an imaginary number, as we expect, so it's got 0 real part, and this is the imaginary part here. And what we would expect for a capacitor is that once it's converted to an impedance, it'll be purely imaginary, but also a minus number, unlike an inductor, which would have a positive imaginary value. So here's VTH and here's ZTH. So as before, we're trying to compare with answers here that are in polar form rather than Cartesian form. So I'm interested to see the magnitude of VTH, which is 2.9332 volts, and also the angle of VTH, which is minus 0.872 or minus 0.873 radians. So let's compare them. It looks like we've got a perfect match there with B. So B is the correct answer here for the Thevenin voltage. And if you had been asked for the Thevenin impedance, there it is there, and you could convert it into polar form if you needed to. So that's probably a good place to stop, so I'll pack it up there.